Okay, dear student, let's see what is there in this question. An experiment is carried out to determine the count rate corrected for the background radiation when different thicknesses of copper are placed between the radioactive source and the detector. The graph shows the variation of the corrected count rate with copper thickness. Okay, Okay, so it is corrected from the background radiation. Outline how the count rate was corrected for the background radiation. So the only method to do that is that you first, like you record the radioactive activity with the help of a device, and you create a graph there. And the background activity, like whatever is the background activity that is recorded, it is subtracted from each and every point on the graph, all the graph. Like let us say it is subtracted from, like this is already corrected by the way, so like it should be 1200. Like here let us say it was 1200 was recorded and 200 is the background noise, so 200 has to be subtracted from all the points. So even here there will be the gap of 200 points. So 1 2 3 4 5, like this. So the actual graph that they got was this, but when it was corrected, they subtracted 200 from all of them, and that is why this is the new graph which is called corrected graph. And 200, by the way, I've just taken the example, so don't get confused from where the 200 is coming. I'm just saying how the background, how the count rate is corrected from the background radiation. You just subtract them from all the points. Simple. I will show you the mark scheme later. Let us move to the next question now. When a single piece of thin copper foil is placed, now this is not the graph of radioactivity. Try to understand. In the graph of radioactivity, like it is n is equal to n naught e raised to power negative lambda t. So it is n versus t, and it is exponential, and it does look somewhat like this. No doubt about that. It looks somewhat like this. But in this case, you have t on the x-axis, time. And here you are basically having the thickness of the copper foil. It's not the time, the rate at which the disintegration is taking place or something. It is the reading on the device and the partition that I'm doing, how many layers, what is the thickness of the layer that I'm using, that is the thing there. So this is actually different from radioactivity. The phenomena is the same, but the graph is not same. So don't get confused now. Moving next now. When a single piece of copper foil is placed between the source and the detector, the count rate is 810. The foil is replaced with one that has three times the thickness. Estimate the new count rate. So thickness is already given here. So it is, we just need to read the graph. It means, so it says that 810 is the count. So where is 810? So this is 800. This should be 900. This will be the 1000. So 900 is divided into 5 part. So 810 will be very, very near to this. Yeah, approximately this only. So it can be taken as 0.25 millimeter the thickness. So if the count rate was found to be 810, it means that the sheet that was blocking it, that was in between that sheet is 0.25 millimeter thickness. Now what after that? Now after this, it says that now the thickness is three times, and tell me the count rate. So it is 0.25, 0.5, this is 0.75. So here we will find the count rate, and the count rate is coming out to be kind of midpoint there. So it will be 300, nearly 380 or something. It should be 380 as the graph is written here. It should be 380. You could be using the ruler there or something. Accordingly, you can find, like you can draw a straight line there. So your count rate will be 380. Let's see if that is what is the answer given in the mark scheme. Okay. Okay. Uh, the background count rate is subtracted from each reading. And yes, this is coming out to be 380 count per minute. Exactly the same thing that we did. Now, moving to the next question. Further results were obtained in this experiment with copper and the lead absorber. Now the absorber is changed. So one is copper, one is lead. Again, it is not about, the topic 12, that is radioactivity and all that. Related with it, but it is not exactly the same thing. Absorber, like Copper, the thickness is 3.5, corrected count rate is 32. And in the case of lead, the corrected count rate is coming out to be 10 only. Comment on the radiation detected from this radioactive source. So, what kind of radiation will it be? Kind of, see, so 3.5 millimeters. See, we can only say that alpha, beta, and gamma are the three radiations. So, gamma is able to pass through everything. Like I think like even through the lead, the gamma will be passing. Gamma can be stopped by using the iron wall, but the thickness of that iron wall should be more than 1 feet. Then you can say that that wall will be able to stop gamma. Otherwise, gamma is not stopped anywhere. So 3.5 millimeter is very small, and gamma will not be stopped there. Clear. Beta is again the penetration power is very high. For alpha, the penetration power is very less. So we can say that in the case of copper, when the count rate is this and the thickness is 3.5, it will not be alpha. That is one thing is sure, that it will not be alpha. Alpha is stored by even using one single aluminum foil layer that we use to wrap our food. So if you're using that also, even then alpha cannot pass through it. Now, so if it is passing through 3.5, it should be beta. It means this should be beta. And if it is passing through lead, it means that it will be gamma also, because beta cannot pass through lead. If beta cannot pass through lead, and even now your device is saying that the corrected count rate is 10, it means 10 is the actual disintegration which are taking place. Accordingly, if I say that yes, then we would be sure that gamma will also be there. So according to this data, it feels that beta and gamma should be there, alpha should not be. Let us see what is given in the mark scheme. Okay. Lead is a better absorber than copper, so it is not alpha. As it does not go through the foil, it is easily stopped by paper. There is gamma as it goes through lead. It can be beta as it is attenuated by thin metal, can go through the thin metals. So it can be beta also because it can pass through metals, and it can be gamma. And the alternative two is not beta, it is stopped by thin metal. It's kind of like you can give any answer there. It means you can say that yes, it is beta, you will get marks. If you say that it is not beta, even then you get marks. Okay, so accordingly, whatever. So these are theoretical questions, you see. So the answers vary. So don't worry about that. Let us now go for the next question and see what is there in 5D. Another radioactive source consistence of the nuclide of cesium decays into barium. Write down the reaction. So first of all, we will see that the atomic number increases from 55 to 56. It means that it is beta minus. Beta minus means that this is CS 55 137. It is converted into barium. Atomic number increases by 1. This is beta, and along with this you always get antineutrino. So this is the antineutrino particle. So this is what is the reaction. As a thumb rule, you can always remember it. Whenever there is beta minus, atomic number increases by 1. Whenever there is beta minus, antineutrino is always there. And whenever there is beta minus, the exchange particle that is used is W negative boson. This is always the exchange particle. I'm talking about the Feynman diagrams and all, but that is not asked in this question. So this is what will be our answer. Let's see. Yes, so the cesium is barium, and then the beta is there, and the antineutrino is also shown. So this is how the question is done. This is Professor Varun. Thanks for watching the video. All the best. See you in the next video. Bye.